Should be all set. Hello, my name is Anton John Delmar, and this is my ECE 176 final project. So for this project, I aim to create a basic ASL translator that would be able to translate the ASL alphabet into text or speech. Um, my motivation for this project was my sister, a speech language pathologist, brought to my attention the issue of auditory impairment. So she works with children who have issues with speech, and one of those issues can include auditory impairment. So it would require the child to use what is known as American Sign Language, other aka ASL. So I was inspired by this issue, and I wanted to create a tool that can help deaf children or maybe deaf people uh, create a tool that will help them communicate with others when there's no translator available. So for this project, I decided to create four algorithms slash models. So I created a k-nearest neighbor algorithm and a logistic regression algorithm, as well as a simple three-layer convolutional neural network and an AlexNet implementation. So my hope was to train these models and see which one is able to classify with the most accuracy and the quickest. So yeah. I will now discuss the code. So we'll start off with my KNN class. So the dataset that I ended up using had 29 classes, but I'll go into that later. For the batch size, I decided to use 256. So that means for my KNN, it takes 256 images from each class. So 7,000 images total. And I chose my K to be 10. So when you initialize a class, you have to pass it the images and the other labels. This function calculates the mean squared error. So you have an input image, and then, of course, the 7,000 images, you have to find the mean squared error between the input image and each image inside that 7,000. So as you can see, our predict label method will take the mean squared error of the input image and all of the KNN images, and then we can get the smallest distances. So the images in the dataset that had the smallest error, and whichever label was the most frequent, that is the predicted label. So yeah, so we take the 10 closest images and whichever label in those 10 closest images, that is the predicted label. So pretty simple. For our logistic regression class, I decided to use PyTorch's NN module because we learned about it in homework 5 and I thought it was very useful and very easy to implement. So I decided to use that. So as you can see, we initialize it. Our class inherits the NN module class. And when we initialize it, we give it the input channel and the number of classes. We have to instantiate the NN module. And then, of course, it's just simple, a linear layer. And we have the weights as well as the bias, WX plus B, affine function. For the forward pass, you simply flatten the image and then pass it through the linear layer. And as we learned in assignment 5, you don't have to take the softmax because I believe it is calculated when you are doing the backward pass for the cross entropy loss. Now we'll move on to the neural network implementations. Excuse me. So again, I'm using the NN module, the Torch NN module. For my three-layer convolutional neural network, I decided to use two convolutional layers and then one fully connected layer. Um, and I use ReLU as my activation function. I also use batch normalization because I figured during training, I noticed that the validation and test accuracies were a little bit lower. So I figured there might be some overfitting, and batch normalization can help with like generalization of features. So I use a little bit of batch normalization as well. So yeah, that's the initialize the convolutional neural network. And I also had made this helper function. So before you get to the linear layer, you need to know the feature size. So this helper function basically just calculates what the feature size is for you, depending on like your input channel or your image size. So that just helps. And of course, the forward pass function, we have our two convolutions and then our fully connected layer. Moving on, we have our AlexNet class. So um, for this class, or for this implementation, I used five convolutional layers as well as four fully connected layers. So we can see convolution five and fully connected layer four. I again use batch normalization with a ReLU activation function. And I also use max pooling because that is what is used in the original structure for AlexNet. And that also helps reduce the spatial dimension, which can help for generalization as well. Again, the helper function, which dynamically calculates the feature size before the linear layer. And here's our forward function. So we have our convolutional layers, apply the batch norm, max pooling ReLU, and then of course the fully connected layers. So now that we know the structure of our models, we can see how they performed. So we're going to start off with the first notebook. So I actually have three notebooks because I used four data sets. For one of the data sets, I didn't create a notebook, and I'll explain why. So the first data set I used was actually a custom data set in which I used a HSV masking algorithm that I created to sort of mask out the background. So it would be just your hand and then a black background. So when I was testing with that data set, I noticed the model accuracies were really high, but when testing with the live feed, it just failed to classify the letters. So I figured it was because the the data set was too small. So it was 2,000 images, 2,700 images total for 27 classes, all 26 letters plus a control class, which was just nothing, black background. But again, when I trained the models and then tested it on a live video feed, they didn't really work that well. So I opted to go online, and on Kaggle I found an MNIST dataset for hand gestures. So similar to like the hand-drawn number dataset, um, like it's a 28 by 28 image and it's grayscale. And there was 25 classes for this dataset. They did not include C because it's a dynamic movement. So when you are signing the letter Z, it goes like this. See? Um, so yeah, that this MNIST dataset did not include the letter Z. So of course, I'll go through. So we import all our libraries and then our classes as well. We have this helper function from the homeworks that's when we're on Data Hub, if you launch your environment with a GPU, you can use CUDA. Otherwise, it will be CPU, and CUDA's a lot faster. And then we have our CSV helper function. So actually, for this MNIST dataset, it uses CSV files. So the first column will be the class label, and then the rest of the columns will be actually the pixel values. So from my 140 class, I actually learned that you can read out CSV files with pandas. So that's what you do in this line. So we get we're reading the CSV file and then we convert it into an image. Um, and it's also important to note that this CSV class is structured in a way that it can work with the torch data loader. So we see underscore length underscore and then underscore get item underscore. Uh, we have to name these functions that because the torch data loader will be using these functions when loading the data. So when we get to our get train val test, we simply pass the file path of the CSV file. And I also, um, the MNIST dataset does not include a validation set. So I took 10% of the images from the training set to make a validation. And so yeah, so we split the dataset, and then we can use PyTorch data loader to load our training, validation, and test sets. And then for our training and test functions, so we have check model accuracy and train model. So these are helper functions actually from assignment 5. I hope it's okay to reuse those. So I reused those to train my models. I did modify the train model function a little bit, so it will save some data so we can plot it later using our plot data helper function. So it'll just plot the training loss as well as validation and test accuracy. So here we are setting up the models. So again, number of classes is 25 because we do not include the letter Z. The image, the images are grayscale, so it's 1 by 28 by 28. So the input channel will be 1 for our CNNs. Um, yeah, and here we get the device. So when I was training it, I used the GPU, so it's a lot faster. And now actually start training the model. Please note that I tested the KNN in another notebook, not this one. So yeah, so starting off with the logistic regression model, I use stochastic gradient descent for the optimizer with a learning rate of 0.01, similar to the homeworks. And in the end, we can see that our logistic regression model got a 67% accuracy on the test set, but the validation accuracy was actually a lot higher. So we can see that in the graph, and the training loss tends to go towards 0. For our simple 3-layer CNN, we got a test set accuracy of 73%, and curiously, uh, we got a validation accuracy of 100% with a training loss of almost 0, as you can see, which is a little bit suspicious. And then for our AlexNet, we get 97% accuracy on the test set and 100% on the validation with a loss of 0. So after training my models on the MNIST dataset, I figured there was like an issue. There was something wrong. And actually, when I tested the models on a live video feed, they also failed to classify the letters. So I did visualize the weights. So as you can see, letter A, B, C, it's pretty good. So this is A in ASL, A, B, C. So you can kind of see it's relatively close. And then I also decided to plot the feature maps of the CNNs as well, just for fun. But yeah, it's a lot easier to see with the logistic regression model since it's just a linear layer with one set of weights. So you can actually see the weights in a spatial dimension. So it looks pretty close to an A here, and a B and C, so on. But unfortunately, these models with the M and IST didn't work. Um, and when I did the live feed, I did apply the transform. So I transformed it into 28 by 28 and grayscale. So that was not the issue. So since the MNIST dataset did not work, I decided to try and create my own custom dataset. So with this dataset, it was 1,000 images per class, so a total of 26,000 images. And I made my own hand gesture for the letters J and Z, because as explained before, Z is a dynamic gesture as well as J. So J is like this, and then Z is like this. So instead, I just use this for J and this for Z. So I made a custom hand gesture for those two letters. Again, we're importing the libraries and the classes. We have to get device, same as before. This time, since my data set was just basic images, we didn't have to use the pandas for the CSV loading, and we can actually just use Torch Vision dset, which has a image folder class that just extracts all the images for you for the data loaders. So again, we split up the images. So I use 80% of the images for training and then 10% for validation and another 10% for test. So we have that. And then here we have a helper function that actually gets the images for our k-nearest neighbor model. So since I implemented that without the NN module from Torch, it was like a custom implementation. I also created a custom implementation to get those 7,000 images. So that's this. So it basically just goes to a folder and then extracts the images from the folder and puts it in an array. Very simple. Again, we have our helper functions, like 5, plot data, and here we have the setup. So this time the number of classes is 26 since I included my own map for the letter Z. And my images were RGB, so 3 channels, and they were also 100 by 100. So when testing our k-nearest neighbor algorithm, we actually got an accuracy of 71.94%, which is pretty good. Our logistic regression model, after training, we got 99% accuracy on the test set and very similar for the validation with the loss of 0. So again, very unusually high accuracies. Um, I also forgot to mention earlier that for each of the models, we're training them for 10 epochs as well. And for the logistic regression model, I use stochastic gradient descent with a learning rate of 0.01. And for our third layer CNN, again, stochastic gradient descent, 0.01 learning rates for 10 epochs. And this led us to get a test accuracy of 99.58% and a validation of 99.77% with the loss going down basically to 0. And for our AlexNet, we get 100% accuracy on the validation and test set with a loss of 0. So again, the trends were very suspiciously high, and it's no surprise when I tried it out on a live video feed, it did not classify the images correctly at all. And when visualizing the features, we can actually sort of see, it's very faint, but you can kind of see the hand. But I believe the issue stems from the data set. So with the data set, how I collected the data was an I took images of my hand at 5 different angles, but I took like 200 images per angle. So I believe what the model did was learn the background. So you can kind of see like the background is very prominent in our visualization. And I can just show an example. So this was the custom data set I made. So for the letter A, you can see here's a picture of my hand. And then I just take hundreds of about 200 images for that angle, and then I switch the angle again, another 200 images, then switch the angle again, So, and you can see like that black frame is present in these images as well. So I believe that it might have been a result of my data sets. So there wasn't enough diversity. Although it was fairly large at 26,000 images, I think that the model just failed when I was doing the live feed because it memorized the wrong features. So it did not memorize the features, or sorry, not memorize. It memorized the background, but it did not learn the features of my hand, I should say. So after that failure, I decided to try another online data set. So I found an ASL alphabet set on Kaggle again. This time it was a little bit different. So again, we have our helper functions. I did have an issue with loading the data set. There was something with the Jupyter Notebook checkpoints. So there's this helper function that helps resolve that issue. But otherwise, everything is the same helper functions. This time, the dataset actually was 29 classes. So they also had their own mapping for J and Z. And they also had an extra three classes to be able to do a space, a delete, and nothing, which is their control class. The images were RGB, so three channel, 200 by 200. We set everything up. So again, we test the logistic regression model. It's important to note, I use 5 epochs this time because this dataset was actually 80,000 images, so I had thought that it would be better than all of the datasets I used so far, but I'll explain why it was not in a second. So I again use stochastic gradient descent for my optimizer with a learning rate of 0.01. Um, and then after training for 5 epochs, it got a 44.8% accuracy on the test set and 65% on the validation. And we can see the loss jumps up and down a lot. It might have been a result of too high of a learning rate. And like the optimizer took steps that were like too big, maybe. So when training the three-layer CNN, we see that the accuracy on the test set was 88% and on the validation set it was 90%. So yeah, pretty good and a little bit reasonable trends. And for the AlexNet, we got a 99.57% accuracy on the test set and another 99% accuracy on the validation, with the loss going very close to zero. So again, I tested the models on a live feed, and they did not classify the letters correctly. Again, despite having really good classification on the data set. So I believe that this issue might stem from overfitting, or I think during training, there could also be data leakage, which is another issue where like the training set might be also learning features from like the test set if like some of the data leaked over into it. Um, and that makes sense because similar to the custom data set I made, I should have checked before I trained on this Kaggle data set. But if we look, you can see there is a background that is very prominent. So when looking at the Kaggle datasets, I found out that they did exactly what I did. A couple hundred images per angle. So here's one angle and then they'll switch. This one has a different lighting, same angle. Um, there's a lot of images and then obviously different angle, different lighting. But since like it's essentially the same image like 20, 30, 50, 100 times basically. since like we can see like all these images present look exactly the same. So I believe that is an issue. So it seems like the model actually learned the background rather than the features of the hand. So yeah. Despite this, I created models that work really well on these data sets. So if I wanted a model to classify on the MNIST or this Kaggle dataset or the custom one I made, I would have three really good models for that. It just doesn't work with a live feed, unfortunately. So despite that issue, I decided to go ahead and test classification speed with the models. Um, yeah, so here's our main Python file where I did that. So I had a HSV detection class. As mentioned before, I initially created my own data set with the masked images, which didn't work out. Um, yes, I've worked with two projects that use HSV detection, one in ECE 196 and one for a hard hack. So I'm pretty familiar with HSV masking. Um, Yeah, we have the get device, and then we have the KNN dataset helper function. And I also have this helper function here, classify letters. So you pass it the model, so whatever model you want to test, so logistic regression, AlexNet, and it puts it in evaluation mode, and then it's able to classify an image. So right now, this helper function actually takes a folder. So I should pull that back up. So we have this. Oops. Yeah, so I made a folder with just some images of letters, and this helper function basically just passes those images into the model for classification. And then here we have our map. So it maps the class number to its corresponding letter. So here again, we have the normal setup, and I decided to use the ASL Kaggle um, dataset that I had just shown. So again, we load the model. So actually, a very useful thing you can do with Torch is that with the NN module, you can actually save the model's weights. So you can do torch.save and save the weights like that, and then you can load it back later. So that was really useful because I would train the models on DataHub, and then I would load them back on here on VS Code for testing with like the live video feed and stuff like that. So as we can see right here, uh, yeah, so we set up everything and we loaded all the models. So the target sentence was, "Hello, my name is Anton," which is 22 characters. So I would basically just make the models classify it and then divide it by 22 to see how fast on average it calculates a letter. And I did this a few times, but uh, I would like to use the results of this one since I did the calculations for it. So when I ran the KNN, it took 19 seconds, and I think it got three letters right, so pretty good. The logistic regression model thought all the letters were the letter F, and it took zero point zero 0.04 seconds. So very quick, but an accuracy of 0%. The three-layer neural network um, classified all the letters as either a G or an H. So again, accuracy of 0%. And it took 5.76 seconds. And finally, our AlexNet implementation, which took 2.45 seconds, uh, it had a combination of the letter X, G, N, and Z. And it actually had an accuracy of 9%. I think it might have just gotten lucky, but who is to say? So ultimately, in the end, I did the calculations. So you can see, so the KNN took about 0.86 uh, letters per second. So it'd calculate a letter in 0.86 seconds. The logistic regression model would take zero point zero zero 0.002. The CNN would take 0.026, sorry, 0.26, and the AlexNet would take 0.11. So in the end, the AlexNet model was my best bet with an accuracy of 9%, and it was fastest. So yes, I would go with my AlexNet model. Unfortunately, when testing with the live feed, it really struggled to classify all the letters. It would only get two or three right, is kind of which kind of makes sense as we can see in the outputs that I got. Mm, I think the main takeaways for this project for me were testing and training the models and seeing how to get the accuracies higher. And I think it was really fun creating my own data sets, 26,000 images. But if I had more time, I would definitely go back and redo the data sets because I believe that is what led to such poor performance on the live video feed. Um, yeah, the method that I used was similar to the data set I found online, and the MNIST was just not that good. I believe for the MNIST, it was an issue with the image size. So 28 by 28 is too small to recognize um like the hands features. And then the custom data set that I created was 100 by 100. So that's also a little bit too small. And for the final one, 200 by 200 was a pretty good size, but it still failed because they collected the data in a similar way that I did with five angles and then 200 images per angle, causing the model to learn the background rather than the actual features of the hand. So yeah, if I had time to go back, I would definitely spend a lot of time on creating a better data sets. I don't think there was issues with the models that I created because I had used them in a homework assignment and they worked relatively well on the CFAR datasets. So I think it was just a matter of really bad datasets on my end, which is quite unfortunate. But other than that, it was a fun project and a very fun and interesting class. And I hope to get into ECE 285 next quarter to take another fun computer vision class with Professor Shalom. So, yeah, thank you for your time. I don't know how to end the. Oh, here you go. Thank you.